So, hi, I'm Dan, and I'm working in Indianapolis, Indiana for Roche Diagnostics, and I spend all of my time developing medical devices. I've spent about 12 years working in Roche, and the majority of my efforts have been spent there in the security domain. So, I think maybe you've heard something from CodenomiCON already today and earlier this week about some new legislation and guidance that comes out from the United States government. So lately the FDA has expressed some pretty definitive concern around the topic of cybersecurity, and they literally have defined this topic now for manufacturers like us when we're going to submit new products into the market. So we call that a 510K or a PMA submission of a new medical device to market. And they're literally now calling out things like the availability of that system, and that manufacturers should consider cybersecurity in the design phase of medical devices, also referencing the existing risk guidance document from FDA. So risk and hazards analysis is something that's extremely well defined in medical, as it is in any other safety-related domain. Things are very serious there, and now cybersecurity is going to be a focus for medical device submissions. So one of these points here is availability, and I guess you've seen these CodenomiCON guys crashing things in the other room, and sometimes I guess that could happen to a medical device if you don't pay enough attention to the topic. So this is a picture of how we're doing that inside of Roche, and you can have a look here at basically our process in terms of development and where security fits in there. So everything begins with an analysis phase where they come up with a concept for some new medical device that is going to help people and better their well-being, or hopefully treat something like diabetes. We have a feasibility phase where we start to build a solution to that problem and help solve this healthcare issue. Then we start development, which is where we get into some coding, and then we implement, and then we build it. So throughout the life cycle of developing these medical devices, we have to look at security in terms of every single domain. So in the beginning, we consider the functional requirements of the product, which isn't really that interesting as it might be for some, because functional requirements in a medical device are more what the system shall do, or how it shall functionally do things. And most of these security topics are rather constraints, and they're very much negative requirements. Risk management is where it begins, and this alludes to what FDA is also guiding the rest of the manufacturers. It's extremely important that threat modeling be done inside of medical devices, especially ones that communicate. And this is where you should realize that your product operates in a context where someone might intentionally misuse that system, and you have to be defensive in your architecture, your design, and your implementation. So, of course, you'll realize this somehow and put the developers on the right tracks, hopefully at your security architecture phase. Then you can review all of their code in your testing. So the rest of my slides are really going to focus on testing, because I figure everybody's here related to CodenomiCON. Everybody's probably into fuzzing. So inside of the fuzzing area, we're talking about the threat model introducing why you might want to use a fuzzer. So perhaps you're going to use a radio interface on your medical device, and there's a risk introduced by doing so that someone might crash the device. It's possible that any untrusted peer is going to behave in a strange way. And this has two potential impacts. So we had a lot of discussion in the last 48 hours, I guess, about things like this. To me, the topic of safety in medical devices, it's a non-issue, because you always have to deal with this. So anytime you're dealing with a device that is maintaining someone's health, you have to take care about all of those bugs. There's a lot of other bugs that you find in security and fuzz testing where maybe they just have a business impact. So the difference might be that the device is not available to help someone stay alive, but on the other hand, it might just fail gracefully or make an annoying alarm or something that they just don't like. So it's important that you don't ignore both of these types of bugs, because things should be safe, but they should also be somehow friendly to the user. There's some example of results you might find, I guess, if you're familiar with radio traffic, you're familiar with these. Every time that you find these kind of bugs, you have to retest everything. So any fix that you put into communication stacks is going to have an impact on the rest. And if, for example, you see one of these anomalies and then the developer fixes that by maybe changing the size of the stack space, that might have introduced another problem because he might have found that stack space by optimizing some other code and introduced a new bug. So the story to me kind of looks like this, where you've designed this really solid, secure communication channel that's proprietary, but you've built that on top of a standard protocol. So maybe you want to interoperate quite a bit with others and other devices, but you also want to do some special stuff of your own, or maybe some proprietary things. And you need to define a threat profile for this. So examples of what you might be prepared to deal with in that space, to me, are going to be some crashes. So someone could make it so that it's just not working anymore. They might jam it, so it might become unavailable for something else to talk to it. They might drain the battery. So it's very common in portable electronics now that battery is kind of the thing that everybody wants to optimize, and it's even low energy in the title of the new protocol names. And that's a difficult problem, but it's one everybody has to deal with. And finally, you can occasionally write or exploit some data. So some of these types of, let's say, radio traffic exploits could at least erase, if not modify, data inside of the device. And you really have to consider everything that's public first. So I think that's the most important thing, that everybody can somehow start this kind of testing with exactly what's going to be the most sensitive part. So if you spend all your time fuzzing inside of your proprietary data formats and stuff like that, and then you ignore the unauthenticated pairing mechanism that exists right before it, you might have missed something. So now I'm going to talk a little bit about some curious adventures that I have kind of doing this kind of work, and some things you should pay attention to if you're going to start fuzzing some portable electronics. So the first thing you should think about is, does it time out? So if it has a radio, there's a good chance that this, again, consumption of battery being a design goal, it's going to want to time out a lot. Second, it's going to need some kind of user interaction. So it's very popular that the device is going to just go into some kind of sleep state, and you're going to have to fiddle with some buttons or some dials, or maybe you have to touch the screen. Of course, it has some battery limitations. You also need to understand exactly what kind of batteries it's designed to use, and if it has some debug outputs. So black box testing, like fuzzing, I guess that's a whole nother talk about how you can debug and get good information. But assuming these are your own devices, which they are in my case, you should be able to also be prepared to get good debug information in order to get constructive feedback about what it is that you've found in terms of bugs. And then you need to consider always, if you work in a Faraday cage, if the guy next to you is using the microwave, it affects the radio traffic so that it doesn't even work, or yeah, you need some coffee, because sometimes it takes a while. So in order to solve the problem of power, I think it's a good idea that you typically want to swap the batteries out and supply your own power. So I've kind of modeled this for like hacker-friendly versions of how you might do this that's not requiring expensive electronic equipment, which of course we have, but I think it's more practical this way. So providing power can be done just very simply by attaching like a microcontroller on there and understanding what the voltage of these batteries is going to be, and also the power. It's also a really good start if you're interested in looking at how battery consumption is affected. So you could, for example, tether your little power supply here to your testing tool, so something like a CodenomiCON fuzzer, and it could communicate with this, and then you could have a look at the power analysis, and maybe you know exactly how much power each test case is consuming. Then you might find the most expensive ones, and you might find some interesting areas to focus on someone trying to drain the batteries out of your device. Sometimes you have to push the buttons. So we've run into situations where, for example, the maximum timeout of the device, or maybe the radio to be in some advertising mode, is just 2 bytes. So that's 255, and then that literally translates into seconds. So for that, you can use some servos, which is one way that I've done it. Servos are kind of noisy, and they'll get a lot of strangers at your desk asking why, like, this robot is always making noise. But yeah, it's pretty effective, and that's the entire way to make it push the button twice for me to avoid this timeout, just using $30 of parts from Radio Shack and some Velcro. A better way to do that is to take the device apart. So if you have the opportunity to break the case, depending on how formal your testing is, and if you're able to do that, taking it apart is much more efficient, and usually pushing some buttons is just pulling ground down to a pin, so you can just solder some leads onto that pin, and it's very much more reliable. You can also control that through your fuzzer, for example, and then you can tell the fuzzer, for example, after each test case, push these buttons, or after you think that something has crashed, you could maybe do a reset sequence and this kind of thing. It's much better than sitting there and fooling around with it yourself, for hours. So then you're going to find some bugs maybe, and then you can decide if it fails gracefully. So some exceptions have been handled, which means someone's going to make a decision in that device. One of your developers is going to decide that device is going to power down now, or maybe it's going to tell the user you need to pull the batteries, or maybe it's going to reboot. But these are handled in a way that, like I say, they could be very safe. So maybe it fails open and everything's fine from a safety perspective, but it's completely annoying that you can't carry your device around at Black Hat without having to pull the batteries every 10 seconds because someone has this tool. You might find, for example, this 8 issues in testing, and then each one occurs 100 times. So I think it's very common that as you get more used to this, or if you're doing a lot of fuzzing, I guess, finding the root cause of exactly why these bugs happen, like if you're tripping up the state machine in the protocol, or if it's actually it's running out of memory or something like that, it's best if you can group these findings into categories that make sense, so that you don't think that you have 1,200 bugs when you really only have like 4. And then you got to fix something. So I'm really not a fan of testing things that can't be fixed. So the fixes for this kind of thing usually go into application code, stack configuration, or some stack code. And depending on where that goes, you may need some help from someone that supplied you some silicon, and they may need to modify a mask ROM. So this can be a little bit strange. It can also be really expensive. Every time that you change these, again, you should run a full regression of all test cases, because anytime you fool around in any of these areas, something else is going to be a trade-off. Most of those older chips are not containing any flash, so they're a little bit strange to fix. Also, if you need to fix them quick, it's interesting how that works, and we can talk about that if you want. But in any case, the newer ones are now system on a chip, and I think that it's going to also change the agility that they have and the ability to fix them a little bit quicker. I think that the most mature way to approach this is always to try and do it in the procurement phase. So when you select parts, for example, if you're into radio parts for some device, maybe a medical device, it's best if you do this kind of activity even before you select your silicon vendor. So usually you can select a silicon and a stack vendor independently, and you can fuzz both, and you can fuzz combinations of both, and select something that's very robust and reliable. And then you don't have the circumstance where it's already gotten into your device and you kind of have to live with it and cooperate to fix it. You can just agree before you pay them that you're going to have a good product. So that's my slides.
Thanks, Dan. Appreciate it.